Okay, so here's the last video component that I'm going to have. We'll go through the write-up for Part 2, Natural Selection. Okay, so remember for this activity, it was, where's my camera here? Where we had this, like these cloths and then these different variations in bean color. So we had navy beans, or these smaller white ones, kidney beans, pinto beans, and then black beans. And then, so like this was a darker background. Some of the tables used like a lighter background, which would have made things different. But in this darker background, I ended up with more of the darker colored beans surviving, and some of the lighter ones were easier to see, even though in some situations the navy beans were harder to see too, depending on where they were sitting on the tablecloth and so on. So we'll go ahead and do the write-up for that part. So the number that survived of black beans was 5. The number of kidney beans was 3. And then we had 1 pinto bean and 1 navy bean survive. So then you can go ahead and just write that data down. I didn't count up how many were removed, but I removed 30 and left 10, and I started with 40 total. So then we can simply just do that subtraction. So since I started with 10 and 3 survived, that means that I removed 7. Here I must have removed 5. Here I must have removed 9, and here I must have removed 9. Okay, so the population that remains, that those beans would then like survive and live another day or a week or a month or whatever, and then possibly able to reproduce and then pass their traits on to their offspring. So our offspring would then theoretically have phenotypes similar to the parents. So if like 3 kidney beans survived, then those 3 might be able to reproduce. And I'm just going to use a multiplication factor of 4. So if I go 3 times 4, then I'll say that, a couple days or months or whatever, weeks later, we're going to have 12 that are kidney bean like variety. And then, so 5 black beans survive, then 5 times 4 is 20. We might have 20 black beans later on in the weeks to come after they survive and then reproduce. And then pinto beans, 1 times 4 is 4, 1 times 4 is 4. So we're not gonna have very many pinto beans or navy beans. And in fact, if this activity were gonna go on further, if we were gonna do another round, we would then start the next round with 12 kidney beans, 20 black beans, and only 4 pinto beans and only 4 navy beans, because the population has, I guess you could say, evolved through natural selection. The predator was able to see and hunt for beans that were, had phenotypes that were not advantageous for survival. And then the ones that had phenotypes that were advantageous survived, and eventually you might come to a situation where, no navy beans or pinto beans or even kidney beans perhaps would survive if this were going to keep going on and on. So for my data here, what was the most favorable phenotype? I would say probably the most favorable phenotype would be that the coloration of the black beans tended to, on the black background, help those to survive and blend in. Why? Because it was camouflage. Oh my gosh, I don't know how to spell camouflage. Maybe that's probably not how it's spelled. They blended in. Why is variation among a population a good thing for the survival of the population? So, we look at if there's a selection, and when I say selection, it's like if there is pressure put on a population due to a predator-prey relationship, due to maybe environmental conditions, what have you, then some individuals will have traits that allow them to survive better. Those traits aren't always bigger, faster, stronger. We always tend to think about that as being more advantageous. But sometimes traits like slower are more advantageous, and sometimes traits like smaller are advantageous. It really depends on the pressures that are being put on that population. But not all individuals have the traits that are advantageous, but some do. And so we're talking about survival of a population. That some individuals will have advantageous traits, help them to survive, and then pass those advantageous traits onto their offspring. Natural selection increases the frequency of beneficial mutations. We talked about DNA replication and how mutations do occur occasionally, very rarely, but they are significant because the DNA genotype is so long that randomly from time to time you will get mutations. Some are good, some are bad, and beneficial mutations might provide new phenotypes in a population. So we can model this concept through maybe addition of a fifth bean phenotype. Maybe we could add a new bean variety. Maybe we could alter one of the beans to have a new phenotype as well, and so on. You could like paint one of them a different color or chop one of them in half to demonstrate a different size or something. All species, number 4, of organisms reproduce. So that is a fact. Like, think about like a maple tree in the spring dropping hundreds, if not thousands, of maple seeds. How many of those maple seeds are going to survive, not get eaten by squirrels, those types of things, and then grow into full-size maple trees that are then reproducing more seeds? Not very many, if any, in a particular season, right? So all organisms reproduce, and in this case, we model that by saying each organism basically produced, we multiplied by 4, right? So we multiplied survivors by 4. So each survivor was able to then pass on its traits to multiple offspring and did more than simply repopulate itself, right? So that's an important factor, that all species of all organisms, including humans, when conditions are favorable, tend to overpopulate. List 3 factors that might cause a population to change over time. This is a generic question, so I guess I'll give a generic answer, like environmental factors like weather patterns, predator-prey relationships, disease, famine, food shortages, food changing in food sources. All those things might cause a population to change over time.